All right. Hello. So we have a pretty short list of problems for today. Nothing too extravagant here. My YouTube preview keeps like getting minutes behind. It's ridiculous. Anyway, just a couple problems for today. So let's get to them. Because once you have sort of the trick for this, you only need to see it a certain number of times before, it just becomes like, okay, that's how this goes. Okay, so let's look at the first integral here, cosine to the fifth of x dx. Right, so this is an odd power here. So since it's an odd power, what we want to do is, just like before, we want to split off. Oops. Sorry, that wasn't supposed to go there yet. We want to split off one of them. We had a fifth power. We're going to pull off one of those. And that creates our... that sets us up to do our substitutions. Right? So we want to rewrite here. Sorry. This is cosine squared of x squared, because we need to get cosine squared in here somehow. And the reason we want cosine squared is because now we can use the trig identity to swap this out. And now we're set up for a substitution. The substitution in this case is just sine of x. And then du will be cosine of x dx. Right? So, oops, I want to switch back here. So, get 1 minus u squared du after the substitution. Right? That look good? All right, then. Sorry. So now to finish this off, we actually have to expand this. So 1 minus 2u squared plus u to the fourth du. All right, but no big deal. We can integrate this now, no problem at all. This will be u minus 2/3 u cubed plus 1/5 u to the fifth plus c. And now we just have to swap everything out. So this is sine of x minus 2/3 sine cubed of x plus 1/5 sine to the fifth of x plus c. And there we are. All right, so that's it for this integral. Nothing hopefully too tricky here. Okay, good. Cool. All right. So let's jump on to the next one here. I'll do this on the next page. So problem 2 here. This one's a little more interesting, right? So we have sine to the fourth cosine squared. So we did one similar to this in the lecture videos. I think we did. Did we? I don't remember now. I think we did sine squared cosine squared. But now I don't remember. But that's okay. We can still do this. Right? So since we have even powers for everything, this means we have to reduce everything. Okay? So the first thing we want to do is rewrite this so everything is in terms of sine squared or cosine squared. So in this case, we'll have this. All right, now we want to swap everything out using our trig identities. So this one is 1 minus cosine of 2x over 2 squared. This one is 1 plus cosine of 2x over 2 dx. Okay, so we definitely did sine squared cosine squared. I remember this now. All right, so now we need to expand this out as best we can. So this 2 here and this 2 here, I'll get 2 copies there, 1 copy there. So we get a 1/8. And then let's start working on expanding this. This is going to be 1 minus 2 cosine of 2x plus cosine squared of 2x times 1 plus cosine 2x dx. All right, and now we're going to multiply this out. So 1/8. Let's see, we get 1 minus 2 cosine of 2x plus cosine squared of 2x, and then plus another cosine of 2x minus 2 cosine squared 2x. Running out of room here, let me move this over a bit. And this will be plus cosine cubed 2x dx. All right. So now we're here. This is what we have now. Let's simplify this because this will look a bit nicer afterward. We have 1 minus. Let's see, we can combine this term and this term. So this is just minus cosine of 2x now. We can combine this term and this term. So this is just minus cosine squared of 2x. And we can deal with this one. All right. So now we're here, right? Now we have a whole bunch of sines and or a whole bunch of cosines, a whole bunch of powers of it. So we need to be able to deal with these. And to do that, well, we have to use our techniques that we know on each part of this. So this cosine of 2x here, we have to change this to 1 plus cosine 4x over 2, because that's the only way we can deal with even powers. And here, this cosine cubed, let's split this off because we're going to use a different technique for this integral. Right? This is going to be cosine squared 2x times cosine of 2x dx. Right? So we're going to get a variety of techniques in this one. Right? So when you start getting like really big higher powers of the sines and cosines, it gets a little more long, let's say. Right? Now the good thing is this first integral here, this first integral is completely ready to go. We'll just simplify it a little bit. So this will be 1/2 minus cosine of 2x minus 1/2 cosine of 4x dx. Okay. Over here, we're going to have to do our substitution with the trig identity. So this is sine squared. Since there's a 2x here, the sine gets a 2x. All right, so now we're looking at this. This first integral we can compute. So this will be 1/8 1/2 x minus 1/2 sine 2x minus 1/8 sine 4x. Now there's normally a plus c with this, but I'm just going to wait until I get the plus c from this integral. Right? So plus, here, as usual, we're going to make this sub u equals sine, in this case, 2x. So this is going to turn into 1/8 integral 1 minus u squared, and this is going to turn into 1/2 du. Okay. So, all right. Let's be a bit lazy about it here. I'm going to duplicate this. All right, so we get all that, and then now we have to integrate this piece. Oh. All right, so integrate this piece here. That 1/8 and this 1/2 will actually turn into 1/16. Here we'll have u minus 1/3 u cubed. And then plus c. And now we just have to plug all this stuff back in. So I'm going to be lazy about rewriting everything again. All right. So here we have u is sine 2x, so this is sine 2x, minus 1/3. Oh, sorry, I wrote sine squared x, sine of 2x, and then minus 1/3 sine cubed 2x. I'll see. All right, and there's a little bit of simplification you could do here if you want. Like, actually, this sine 2x here and this sine 2x here are actually going to end up canceling each other out. But this is fine. Here, we can just leave the answer like this. Yeah. All right, you know what? I got to do it. 1/16x. All right, so if you multiply this out, this one will give you negative 1/16 sine 2x. This one is positive 1/16 sine 2x. So those cancel. Here we have minus 1/64 sine 4x. Here we get minus 1/48 sine cubed of 2x plus c. So this is the simplified form, or at least a simplified form of the answer. All right. So, any questions on this one at all? All right. Hopefully that wasn't too bad. Sorry about that. All right. Just it's not letting up right now. All right. 3. You want integral of sine cubed x cosine negative 2x dx. All right. So this one has a little bit of a different look than the other ones we did, because we only talked about things with positive powers. But as it'll turn out, it actually doesn't matter. As long as one of the powers is negative, we're going to have something pretty straightforward to do. Or sorry, not negative, odd. So here we have an odd power. We're going to do the exact same thing we've been doing, right? So here, same thing, sine squared x. I'm going to put the cosine over with it, and then I'm going to put the sine at the end here. Right, that extra sine I peeled off, I'm putting it at the end. No, you don't have to do this. I just find it a little easier to look at this way. Right, and then what we're going to do is swap everything over to cosine. Right, so now we're here. And we're going to do our usual substitution. U is cosine of x. Du is negative sine of x dx. Right? So now that we have that, we can just compute this integral. Or sorry, we can do the substitution and then compute the integral. So we have 1 minus u squared. Here we have u to the minus 2, and sine x dx turns into negative du. So if you multiply all this out, you'll notice what we get is actually 1 minus u to the negative 2. Right? And so this one doesn't turn out too bad. Right, so let's see. Integrate this. We have u plus u to the minus 1, actually, that's it, plus c. So what this is cosine of x plus secant of x plus c. Right? Not too bad there. Any questions about this one at all? Okay, great. So let's look at problem 4. Right, so here we're looking at sine of 3x, sine of 2x dx. Sorry. Okay. Here we are. Let's see. So, remember how we deal with these. Okay, there's these trig identities we need to use again. So if we have 2 copies of sine here, what we turn that into, remember we had the trig identity, where should I write it? I'll just write it right here. Actually, I'll write it right up here. So remember, sine of A, sine of B, this ended up being cosine of A plus B minus cosine of A minus B. I forgot to put in the 1/2, so I'm going to just divide this by 2. All right, so we use this identity here to switch out this integral. All right, so I'm just going to pull that 1/2 out to make life easier. So this is going to be cosine of 3x plus 2x. So that's cosine of 5x, right? And then this one, we're going to have minus cosine of 3x minus 2x. So that's just minus cosine of x. Right? And then now we just do the integral. So it's 1/2 of 1/5 sine of 5x minus sine of x. And then plus c. And that's it. Oh my god, please draw the box. Thank you. All right, that's all there is to it. Hopefully that's not too bad. Hope that makes sense. Any questions about that one? Oh my god. So these problems here, they just come down to using the appropriate, identity here. Whether it's a product of sines, product of cosines, or a mixed product. All right, so the last one here, I was mentioning in the lecture videos that this has something to do with sort of Fourier series. And the way it really has to do with that is through integrals like this. This is how you compute what are called coefficients of the Fourier series. Sine mx, or sorry, I'm jumping ahead of myself. This isn't exactly what coefficients are. This is how you compute, how you show that all these different waves are actually what are called orthogonal functions. Right? So we have to do this integral here. And conveniently, I have sine and sine again, so we can use that same identity. And we know this is going to be 1/2 integral from 0 to pi of sine. So we're going to have mx plus nx. So here that's m plus n times x. And then minus sine of mx minus nx, which is now what I want to do here is show you sort of the 2 different outcomes we can get here. Right? So we're going to do this in 2 cases. Right? So let me call this I. Right? Let's look at case A. M equals n. If m equals n, then I is going to be 1/2 0 to pi. Right? This one here is going to be sine of 2x. Here we're going to have sine of 0, which is 0, so we don't need to do anything else. So we're doing 1/2 integral from 0 to pi of, I don't know why I'm rewriting this. Right? So we're integrating sine 2x, so this is minus 1/2 cosine x, cosine 2x. Right? And this goes from 0 to pi. So now we just do that computation. Minus 1/4 of cosine of 2 pi minus cosine of 0, right? Oh, 2x. Okay, no, we're good. Right. So, compute this integral. Have I done this right? I feel like I've messed something up here. I have. I've really messed something up. These aren't sines. These are cosines. I was like, this answer shouldn't be 0. All right. Let's just let's try that again, but with being less bad at it. Okay. So sorry, this is cosine of 2x minus, and here this is going to be cosine of 0, which is 1. Sorry, I had a feeling this was feeling off. Oh boy. All right, let's try that again. Oh, sorry, I don't know why I wrote 2x. This is 2mx. This is still minus 1, though. I'm just making all the mistakes in this problem today. All right, so let's just talk through this one real quick. All right, so m equals n. So I have m plus m. May as well call them both m. So I have 2m times x here. Here I have m minus m, so that's going to be 0. Cosine of 0 is 1. Okay. So now let's try integrating this, and hopefully not doing it wrong this time. All right, so integrate this. We're going to have 1 over 2m sine of 2mx, and then minus x. Okay, so we integrate this, and we're going to have 1/2, or sorry, this is from 0 to pi. So plug in these things. We get 1 over 2m sine of 2m pi minus pi. And then here, if I plug in 0, I get sine of 0, which is 0. I plug in 0 here, that's just 0. So we'll just kind of spare ourselves here and just write minus. Right? Now, sine of 2m pi. So that's either saying sine of 0, sine of 2 pi, sine of 4 pi, 6 pi, or negative 2 pi, negative 4 pi. At any rate, whatever this is 0. Whatever m is. Okay? So what we get here is have I messed up a negative sign again? No, I don't think so. It is minus pi over 2. That's not right. What have I done? These are in the wrong order. I'm sorry, guys. These are in the wrong order. Actually, this is negative here and plus here. So I have to fix the signs in. Sorry. I'm glad this is the last problem for today. Okay. So let me do this. Let me switch the order here. One should be the minus, this one should be plus, which means these go in. Which means we'll just you ever just have those off days? That's me today, apparently. All right. Let's try this one more time. Okay. I hope I didn't get this identity wrong last in the lecture video. So it has to be a minus b minus a plus b here. Okay. So when we do that, get this identity. If m were to equal n, this one would be cosine of 0, so that's 1. And then this one would be cosine of m plus m times x, which is cosine 2m. So now we do the integral again. Hopefully do it right this time. Minus 1 over 2m sine of 2mx from 0 to pi. Now let's plug this stuff in. 1/2 pi minus 1 over 2m sine of 2m pi minus, and this time again, when I plug in 0, I'm going to get 0 in both spots here. So we'll just call this 0. Right, and for the same reason as before, this is still actually 0. I didn't mess that part up. So yeah, so we get pi over 2, a positive number, which actually makes sense. Okay. Whew. All right, now let's try this again with part B. Hopefully this one only takes one go. Part B. Just want to point out real quick, in question 4 up here, you just have to multiply the answer by -1, since this was just off by a negative sign. Right? So part B here, we're looking at the integral when m is not equal to. Right? This is the interesting one, because I is going to be 1/2. Right, so I doesn't change this time, actually. So what I'm going to do here is just copy this. So now, in this case, we actually just have to compute the integral as is. Right? That wouldn't work if m equals n, because we'd be dividing by 0 with this part. But that's okay. That's okay here, because this is no longer 0. So let's do this integral. So we're going to have 1 over m minus n sine m minus nx minus 1 over m plus n sine of m plus n x plus c. Right? So Oh, sorry, not plus c. What am I doing? Continuing to have a bad day, apparently. 0 to pi. And now we just plug all this stuff in. Right? But there's something interesting that's going to happen here when I plug these in. Right? So I'm going to get 1 over m minus n sine of m minus n pi minus 1 over m plus n sine of m plus n pi. Right? And when I plug in 0, I'm going to get sine of 0 and sine of 0. So again, no reason in pretending that this isn't just... All right, so what's going to happen here? Well, this here, this is going to be sine of some integer times pi. Right? So here, I guess I should have specified this at the start. M is an integer. Well, m and n. I sort of forgot to put that in here. Hey. All right. So that is an important fact because that means that this sine of m minus n pi, this has got to be 0 no matter what. Because it's either, 0, pi, 2 pi, 3 pi, or minus 2 pi, or something like that. Because m minus n is some integer. Likewise, this is also 0 because m and n have to be whole numbers, right? Or have to be integers. So they can be positive, negative, or 0. So hopefully you can see here that, well, actually all of this just turns out to be 0. Which is kind of interesting, I think, that we can say, if I have sine mx times sine nx, so m and n are integers here. It's pretty interesting to be able to say if those two integers don't match, then that integral has to be 0. It's kind of an interesting fact that. And on the other hand, if they are the same, that's the one case that the integral isn't 0. Right? So this has to do with a concept in mathematics called orthogonality. And what we've shown here is that these two different sine functions, sine mx and sine nx, form an orthogonal family. Right? So they're obviously, with themselves, they're not equal to 0. But if we choose two different values, we get 0. Right? So hopefully, despite the mistakes there at the end, hopefully there's something interesting you got out of this one. And with that, have a great weekend, everyone. I will see you Monday.